In this video, we're going to take a look at the diode equation shown here in the middle of the screen. We're going to look at what kind of IV characteristics this equation will give you and explore what some of these different variables mean and their impact on the IV characteristic. So this is the Shockley diode model equation. So this is for an ideal diode based on a p-n junction, so such as the very common silicon p-n junction diodes. And what it gives us is a relationship between the diode current and the voltage across that diode, Vd. So of course, by plugging values into this equation, we can get the IV characteristic of a diode. So that's shown here in the middle. You can see that we have the voltage Vd on the x-axis and the current I on the y-axis. And this is the kind of IV characteristic that we would expect for a diode. It's allowing almost no current when in the reverse bias, and there's a certain turn-on voltage at which a large amount of current will begin to flow. So that's our diode behaving kind of like a valve in the circuit. So this is the diode IV characteristic that you'll get if you plug values of Is equals 10 to the minus 11, a Vt of 26 millivolts, and an N of 1 into the diode equation. But what do these different variables mean, and what impact will they have on our IV characteristic? So if we start with Is, so Is is the reverse saturation current. So this is the magnitude of the current that you'll get when you have your diode under reverse bias. So when we look at this IV curve by eye at the moment, on this scale it appears to be zero current when there's negative voltage. If we were to zoom in quite a bit onto this part of the IV characteristic, you'd see that you actually have minus 10 to the minus 11 amps as your current in that region. Of course, it also has an impact on the rest of the curve. As we can see, it's here on the outside of the expression. So what happens when we change our Is value? You can see here, as we go from 10 to the minus 11 to 10 to the minus 10, the IV curve shifts slightly to the left. So if I go back there to the minus 211, you see it on the right. As we go over to minus 10, it shifts to the left. So Is also clearly has an impact on your turn-on voltage for your diode. So next, let's take a look at Vt. What does Vt mean? So Vt is the thermal voltage. So at room temperature, this is often taken to be 26 millivolts, and sometimes people will use 25 millivolts as well. And the value of Vt actually comes from another equation, quite a simple one, which is Kt divided by Q. And in that circumstance, K is equal to the Boltzmann constant, Q is equal to the charge on an electron, and T is temperature, and that's in units of Kelvin. So of course, T is the variable parameter there, and of course that will then have an effect on your thermal voltage. So we can expect the value of Vt to change as our temperature changes. So as our diode heats up in our circuit, that will change Vt, and that will change the IV characteristics. So here we have 26 millivolts, as I said, typical for room temperature operation. But what will happen to our IV characteristic if the temperature increases such that we get 30 millivolts at Vt? So if we increase that there, you can see that there's a slight shift in the right hand side of that curve. I'll just go back there, that's at 26 millivolts and shifting to 30 millivolts. So it will move our turn-on voltage of the diode over to a slightly higher value. And of course it will also have some impact on the shape of this curve and the diode characteristics. So finally, let's take a look at N. N is the ideality factor. So the ideality factor is in this part of the diode equation here, and this is basically saying how perfect is your diode. So if we have an N of 1, then that assumes that the diode is pretty much perfect. It can be modeled using this ideal Shockley diode model here, and it will follow that behavior exactly. But when we look into the semiconductor physics of diodes, that model is based on certain assumptions about the way electrons and holes recombine within the material, and there are other recombination mechanisms that might happen that are not included in those assumptions, so could slightly invalidate this model. So an easy way to kind of manage that is to have this ideality factor, so that your real life diode, whilst it might not be perfect, you could find the n value that best approximates it and gives you the correct model for that diode. So here we have n equals 1 with a very nice diode characteristic. But what if we increase n up to 1.5? You can see that's got quite a dramatic effect on the turn-on voltage of the diode. This is perhaps something a little bit more like what we might expect of our silicon diode. Now we're closer to 0.7 volts for our turn-on voltage. And there's also been a bit of a change in the slope of that curve there. So we've really moved away from the more ideal diode that we were aiming for with this model. And for the case of silicon diode, we would expect n to be somewhere in the region of between 1 and 2. So that concludes our summary of the Shockley diode model equation. So we've covered what each of these different variables are and how they might impact your IV curve of your diode.